All right. Hello, everybody. Tonight we're going to go through a little design exploration of our own robot in season. So, this is our 2025 robot Gamma Ray. And we're going to go through and explain everything, kind of how we designed stuff, and what we still have left to do on some things, um, and look at how a lot of the different mechanisms work and how and why we designed some of the things and some of the design choices that we made going through it. So overall, we wanted to make a robot that was able to play Reefscape in a lot of different ways. We're a little unsure with exactly how the game is going to play out. There are a ton of different tasks in the game that teams can do, and which of them become the most valuable are all things that we may not know until we see the game play. And as the game advances, different things may become valuable. So we wanted to make sure that we didn't have too little of a robot to be able to do all of the various tasks in the game, as it's kind of how we felt like we did in 2023 in the last pick and place game. We didn't quite have enough robot to be able to do some of the things that became important as the game went on. And so that meant making a robot that can do a lot, and potentially do some things that we aren't even planning for or things that we're not currently optimized for, but it might do them, or we might be able to adapt it to do it, if it becomes important. So this robot's basic structure is something that could work in a lot of different games. If you change the end effector, like the claw out here, and it picked up cubes, this robot or something similar to this could also play the 2018 game. If you put something on it that could pick up cargo and hatch panels, it would probably play the 2019 game pretty well. In general, this sort of basic archetype with a elevator and the double jointed arm and an end effector at the end can play most pick and place games in some way. Like you have enough positional freedom that's just designed in mechanically that you can then just add the controls for to allow it to do a lot of different things without having to change the hardware. And that was one of our goals, is we didn't want to have to like do a ton of prototyping to make sure we got exactly the right height and angle and things right to be able to score on the reef. Instead, we could build something that we can just change those angles in software, and it can score in every position that we need to. It can score a level 1. It can pick up from both sides. It could do anything that is potentially useful in the game. It does mean that there's a lot of mechanical things that have to go right for it to work, and then a lot of software on top of it, to make all of that stuff actually happen. And that's what we're working through right now, is a lot of the software. So like most mechanisms, our robot is divided in, or like every robot, our robot is divided into mechanisms. We started out with 5. We ended up combining 2 of them, that we'll get to in a little bit. But the main mechanisms are our drivetrain, our C, which is our sideways elevator and arms, the corral, which is our basically like the end effector, which includes the twist and the claw at the end, and then what we're calling the incline, which is both a climber and a ground intake for algae and coral as well. So like most things, we'll start from the bottom. So we're going to go down to the drivetrain. This is relatively generic drivetrain. This is pretty much the same drivetrain that we ran last year, except for not having an under bumper intake. So we're 29-inch square to the aluminum rails, and then we always give ourselves about a quarter inch on each side to put gussets and plates and things. So the actual drive frame is about 29.5 when we do our frame perimeter. That's what it'll end up being. We drop it a full inch from the normal standard Mark IV-I kind of normal 2x1 playing here. We just have this 1x1 that we did last year too. It gets our belly pan very close to the floor. Lets us lower the center of gravity a little bit by having the battery lower. It just gives us a lot of room. And it's relatively easy to do. You just cut up some 1x1 and have longer bolts going through this warp module. So it doesn't take away anything. There's no cable bumps or anything on the floor, so we don't need any ground clearance again this year. So just slamming it to the floor as close as we can go helps a lot. We run the grip lock wheels, so they do have that suspension, so that means our chassis is even lower to the floor than it actually is in CAD. These plates get within under a quarter of an inch from the floor when we're actually driving around. So that makes it very, very stable. For the most part, there's not a lot of places you can go. As soon as you rock a little bit, you're up onto, you hit the frame pretty quickly if you start rocking it all or anything. Um, in addition, it did let us get this done pretty quickly. We didn't have to design a lot. That's one of the bigger benefits of Swerve is you don't have to spend a ton of time designing your drivetrain. We can just throw some rails in, do the tube converter feature scripts in Onshape, and we're all set. In addition to that, we've simplified our superstructure mounting over the last couple years, taking inspiration from 3538 Robo Jackets by having our top rail. It's just a set of 1x1 that runs all the way along, and it means that we're able to mount most of the things up above the swerve modules without having to mount like around them. It gets kind of weird to mount into the corner sometimes where the swerve modules are kind of cut out here and you don't have this 2x1. So we're able to mount everything up to this 1x1, and we don't have to come down nearly as far. So all those plates and things can be shorter. They can be structured off of this. If we need to swap these, it's a lot easier to. Gives it a little bit more backing for the bumper and things too, so the bumper's not just fully cantilevered off this lower rail that's super low to the ground. We can have the top of the bumper backing be up here. We'll be able to like pin through and mount the bumpers pretty easily into these rails this year. We have places for handles. Yeah, just in general allows it to be a little bit easier to mount some things. You can put plates on both sides all the way into the corner, which you can't do all the time if you just do it on the swerve modules. You don't have another. It's not very easy all the time to get this other side plate. So depending on what you need, we didn't really have too much of the use for it this year specifically, but it's just part of our kind of generic Spectrum robots now because we know it makes life easier. It allows adding things, adopting or adapting things quite a bit easier throughout the season. Um, Electronics this year are rather easy. Standard belly pan 0.09 aluminum that we got made by Fabworks this year. Um, we don't do a lot of lightning in this or anything. We like it being relatively heavy. We didn't go steel. We knew we were going to need the weight, but we still need the nice structure of a base down here, super low to the ground. It helps our CG be a little lower. You could cut it all out and have like the diamond cuts that other teams do. Um, but this kind of forces us to keep at least a good amount of weight down as low as we can to offset the weight that we have up higher. It also makes it very easy to mount electrical. We don't have to pre-plan basically any of that. We just VHB tape all the electrical down. We did plan some things for battery mounting, but in several different places. By the time we were making the belly pan, we didn't know where exactly the battery would be. We were pretty sure it'd be down here, but we didn't know that for sure. So there are some different mounting holes for battery mounting that we could have used, basically on either of these sides, or down here, or in the middle if we needed to. This side is left for the elevator, so we did have some stuff pre-planned for that. So those three are for tube end caps that we'll see when we go into the elevator. And then the battery box is super simple this year because we can just lay it down. We just have three pieces of plastic kind of framing it in, and there's a battery strap that goes around it. And then the battery will plug into the main breaker over on this side. And then most of our controls and things are over here. RoboRio, radio or switch, things like that are over on that side. And then I think there's a mini power module. It's not Crichton CAD, but it's over on this rail. And there's another one, I think, over on this rail on the robot as well for powering the swerve can coders, the limelights, and a few other things. We do have the two limelights mounted here. They're kind of low set, kind of inside this our top rail frame that will have a whole polycarb cover on top of it. And so that prevents coral from falling into it. It also protects all the electronics from coral, but it does have some cutout so the cameras are able to see through without seeing any of the polycarb. So we didn't get any glare or reflection or anything like that going into the camera. So it's fully cut out. We're using that same cutout to be able to reach in and touch our main breaker. So we don't have to have a separate cutout for that. All relatively sort of standard fare for our robots. Um, the pigeon is mounted directly in the center to give us the best possible rotation accuracy. It can be off center, but it does get a little bit worse if it is. Um, and then the couple other things will get mounted to other places that are just in here for CAD. So we have our radio, it'll be mounted up on the elevator. And then this is the mount for the Quest, the Meta Quest that we'll have on the robot, at least logging data to see if we're going to need it later in the future, to see how well its camera and visual pose tracking is going to work for us. Moving on. Oh, we didn't talk about the swerve at all, or we didn't talk about the last bit. So we are on L2 MK4i swerve. L2 was kind of our standard ratio for 2022 and 23. And then we went quite a bit faster last year when we knew it was going to be such a full field game and would be running back and forth so much. Since this game is down to mostly quarter field cycles, you're going from loading station to reef and from reef to net most of the time. We don't need that high end top speed very much that the L3 Plus gave us last year. L2 should be fine for most of our things this year. But this is also a year where like gearing doesn't necessarily matter a ton. The motors have a lot of torque. There will be some people who are on like L1 plus. There will be some people who are on L3. It's not a year where it's going to matter and really determine how well you're going to be able to do. Last year, if you were too slow, it was really noticeable because you're doing those full field cycles. This year, on that quarter field, you're losing such a small amount of time if you're not hyper optimized on acceleration or anything that it's not nearly as big of a deal as it was in the past. And you'll see teams doing different things this year too. Okay. Next up is our C mechanism. So this is the elevator and the arm power and all the arm powering and everything. So this is a pretty complicated mechanism. There are a lot of parts. I think there are I think we're up into the almost 90s into the part numbering, at least like 84, 85, something like that. So there are a ton of parts on this that all have to work. This is pretty much the core of the robot. Without this part, the rest of everything wouldn't do what it needs to. It can kind of be broken up into two different parts. We have the elevators and the arms. So the elevator is. Oh, let's unhide some things here. There we go. So the elevator is a single stage elevator. A relatively simple design in terms of what the mechanics do. There are two there's two motors down here. There's two Krakens driving these two gears, and they're connected together so that both motors are staying in sync with each other. So in software, we just control this motor, and this motor is just in follower mode. So we're just getting the power of the two motors. They're basically kind of acting as one. And then each of those, this same shaft here, has a 36 tooth pulley on it. And on there are our two belts. So these are two individual belts that are separately tensioned and everything. We didn't try to do any sort of like single continuous thing or anything. When it's all the way down, you can kind of see the belt path pretty easily here. So the belt runs from the pulley up around this first idler. These idlers are, we took some inspiration from 2910's 2018 robot. So they used these same kind of bearing stacks, and we could put some washers on the outside and just used pushed on retaining rings to make basically a fully COTS idler. So these shafts on the inside too are just a McMaster part. So we didn't have to buy, or we didn't have to make any, we didn't have to turn a ton of shafts for these or anything. We could reduce our work a little bit, and all of this is relatively cheap. The bearings are under $1 a piece. The shafts are like $1 something a piece. and they seem to be holding up very well. They're come pre-tapped, come cut to the right size already because this is just a 2-inch gap here. And then we have a couple places where it's a little bit bigger, or the gap's a little bit smaller, but we could also get those same um, standoffs there as well for this one up here on those plates. So the belt goes around, it comes all the way up and over our top idler assembly up here, and then it comes down to where it actually does the lifting. Let me see if I can make CAD show us that a little bit easier. Let's hide some things. Actually, what's the easiest way to do this? Not that face. Do it on like this face. All right, there we go. Okay, so in between our two tubes, we have this small plate here. And so this is what is clamping the belt for the up pull. So the belt gets clamped to the tube. It goes on the, like, it's on the other side of this belt here. It just can't be done in CAD. It's on the other side of the belt. All the little belt teeth go into these little slots, and it gets bolted to our 2x1. We're able to bolt it to the 2x1 because we have a little plate inside the 2x1. So we have this little plate here that we had Fabworks make several of these as well. We water jetted some ourselves as well. And then these are just all tapped holes that we're able to secure the part to the tube, and then we'll have all of these holes available for actually clamping the belt down. We do a lot to make sure like the parts are symmetrical and things. Some of the first versions of these weren't, but now this part is just fully symmetrical, so it can be flipped around. It doesn't matter. Same with this one. And so we can use this in a couple other places too where we need it. So I think we actually have one. Yeah, we have one over here. So we were doing some mounting that goes on to the actual mounting of the stationary rail here. We use that same part to be able to do that, to have some bolt holes here for this L that holds it to our crossbar. So that's a relatively simple part that helps us do that. Similarly, we added some like little sections with tube end caps and things to be able to get inside of the elevator quickly. We didn't want to have to do any machining on 2x1 anywhere. So this is all COTS 2x1. We didn't have to do anything except cut it to size. And so that's a lot easier for us. Like, we have the router, we can do things on the tube jig if we need to, but it just takes a lot more time. If anything breaks at an event, or if you have to make a spare or anything like that, having it just be the standard COTS rails is way easier for us. And just more efficient with our time. And so this elevator was pretty quick to put together and build because it's all just COTS parts for the most part, plus some relatively easy sheet metal pieces and things we could get from Fabworks and kind of flat parts as well. Okay, the other part of the elevator belting that I didn't finish talking about. So this is where the up pull is clamped. The belt runs around the pulley the other way, has its idler here. This is spaced in such a way that the belt can't slip off at all. So even if it goes slack, it shouldn't be able to slip here unless something really bad happens and we start bending a lot of stuff. It comes up along the side of our arm motors here. And it will end up being tensioned inside of our little tensioning plate in the middle of this assembly. So we have one more idler that it runs over, and then it runs onto this hex shaft that is inside of, that has this ratchet mounted to it, and this ratchet is between a couple standoffs. And so when the switch is in one direction, we're able to turn this hex shaft that has it has a hole that's tapped through it, and the belt is bolted to the hex shaft. So as we turn the hex shaft, the ratchet clicks over and over again, and it allows us to tension the belt and pull up all the slack on the belt and basically wrap it around this shaft, and then the ratchet doesn't let it unwind ever. So that's how we're able to keep this belt in tension, so that as the pulley moves, all of that motion is translated directly into the elevator, allowing the elevator to go up and down very, very fast, um, without any slipping, and without any damage or any play or any looseness or anything like that. The belt is run inside of the tube profile and everything, so we don't have to worry about it getting caught on things, like we did in our 2023 robot where we had the belt external. And then we do have the belt on both sides, so it's a very even pull up and down. Um, Part of this is based on an elevator that Elliot from 111 posted in the off season. He had a plate kind of similar to this that we took inspiration from. This allowed us to have a very easy place up here to kind of adapt to the tubes and still put our idler pulley in the right spot. So then these are all tapped as well, so we can bolt in our A-frame flanges that also act as our hard stop, and then the rev elevator blocks as well, onto another little section of 2x1, so then we can just rivet into the side here, and sort of just basically make imitation machine 2x1 without having to machine any of the tube ourselves. We went with these rev blocks instead of some of the other ones where they were like on the 2x1, or they only had like the 1/4 inch gap and things, just because the extra space we had the room for in the design, and this gives you a little bit more flexibility with putting things inside here if we need to. If we needed to have something mounted inside here, we could for something really fast, um, or if we just need to get in and do maintenance and things. um, the belt just has a little bit more room to move. You can like put your finger in there and check its tension a little bit. If it's too close, you can't do any of those things. And they seemed easy enough for maintenance. You can take them off with a couple bolts. We drilled through one of these comes tapped. We drilled through that one, so they're both just through holes, so we can bolt them straight into these plates. So we can swap them in and out easily, with just a couple screws anywhere we need to. And then overall, it's pretty much a standard elevator. Um, on the back side here, I guess you can't see it until we have the whole arm, but we did have to be a little bit lean with how we put our back support back here, as when the arm comes all the way up, it doesn't let us have a ton of room as it passes right here. So we have some wiring and things here. So the gap here is pretty small, so we couldn't just put a normal 1x1 or anything here, 2x1. So we do have a pretty thin piece of aluminum there. I think we have a 0.09 or an 1/8 inch piece of aluminum there right now, kind of holding things together. And then if we need to, we'll be able to add more crossing it besides just our sponsor panel, which is going to be on the back. And then we can also cross from this back 1x1 to here as well to support it even more. Um, and then on the comp robot, it hasn't been done in CAD yet, but this tube here, this 1x1, is now an L, so it's one of the Rev L pieces, and so this allows the wires to have a little bit more room and allow this the lower bearing block to come back in. This bearing block right here was kind of crunching the wires because they were trying to go right between it and this 1x1, and there wasn't quite enough space. So we moved that to an L, and now this freely moves up and down a lot easier, and the wire chain, or just the wires in the wire sleeve, have a much nicer path there than they did before. All right. That's most of elevator. We did do some different material choice things, just playing, just kind of learning and doing some things we're not sure about. This is Max Composite because we knew it could pretty much be anything, and Max Composite is light and stiff. This could have easily been aluminum. It would have weighed a little bit more if it was, and it's relatively small, so it was easy enough for us to just laser cut out of Max Composite. It was faster for us to produce that way, so that wasn't really an issue. Um, These plates had to be thinner, so we did go ahead and make those metal so that they didn't hit into the chain or anything here. And they're backed by the Max 90s so much that they're a pretty solid structure there anyway. They don't need a lot of their own stiffness, so those can be pretty thin and can still be light. And then we did the same thing here. These had to be a little bit thin as well to make sure we didn't have these bolts coming too far into where the chain runs here. If we made this plate too thick, you'd start running into the chain for the arms, and so we didn't want to do that. All right, so let's start talking about the arm setup, because this is where the robot definitely gets more confusing and definitely less standard than some of the other robots we'll be seeing this season. So there are two arms. So we basically have two joints. We have the shoulder joint that's run by this chain and this motor back here. These are interchangeable right now. They're the same gear ratios. These are Krakens into 20-to-1, Max Planetaries into the Max 90s. It doesn't really affect us which way the chain goes. There's a few small details where it does, but they could be swapped if we needed them to. This one is for our shoulder. The opposite side one is for our elbow. They're both again the same all the way at the top two. They both go to a 72 tooth Rev billet sprocket. This is all running 25 chain. And so this is how we actually get the arm motion. This allows us to keep the motors relatively low most of the time until we raise the elevator. And so that keeps our weight down a little bit. The double Max 90 side by side packaged much nicer than any sort of custom gearbox we could do that wouldn't hit the chain. The motors are wider than the 2x1, so if we start flipping them out, there's pretty much no way to have them not be in the way of where the chain is. We could have gotten them down under it a little bit and had the chain start a little earlier. We had some sketches for things. We know this works. It's quick. We had a lot of the parts already. And it was reliable. Our 23 and a half robot used the Max 90s and Max Planetaries for its arm as well, leading into a chain reduction, and that worked great for us. So we decided just to do what we already knew and continue down that way, and not put in the time or effort to make anything more custom than that, since this fits so nicely and easily already. Up on the tensioner plate here, we actually had to do several revisions of this. The CAD's a little weird right now. It doesn't have that one mated, but it's fine. Basically, the arm chain, each one of them, there's two different tensioners here with a sprocket on it. And this sprocket's able to be on the opposite side of this chain. And originally we were just planning to have this ratchet here and be able to push through with the ratchet to be able to tension the chain. The original ratchets we bought were only 72 tooth, which ends up meaning that you have like 5 degrees between each click of the ratchet, and that wasn't enough to really tension the arms in the way that we needed to. But what we figured out relatively quickly is we could just run a turnbuckle from this shaft down to this one, and we can just tighten that turnbuckle, and that'll pull the sprocket into this chain, making the length the sprocket has to go longer and making the chain nice and tight. So again, similar to the tensioning of the belt, we're always trying to make sure that any amount of movement from the motor moves directly into the arms in this case, so that we can control them really nicely. So that tensioning system seems to be working out in all of our testing so far. We're able to just have that tighten up that turnbuckle and apply more tension to both sides. So there's one on this side for this sprocket. There's another on the other side with this arm kind of up there tensioning the shoulder sprocket. And that's working out pretty well for us so far. Coming up here, there are a few little details. There's a lot of little details, so this is going to take a little bit. the plates like this are here so that we can easily run wires into the middle of our max spline tube without having those wires ever get near the chain and sprocket. Like, we never want the moving parts to touch the wires and hurt anything. So our wire path basically just runs up here, dives under and sort of behind this plate, comes around, then goes on top of this, and then goes through this hole out through the middle, and then the wires can come out on this side and go onto this plate. And then they actually do a little, they go through this little gap right there that we cut into this part of what we call the bicep. This is the first arm that we have. And then they go back under this other one onto this plate on the inside here so that the wires never touch like this chain or anything. And then through the other tube into our forearm where the motors for the twist and the claw are out there for corral, which we'll get to in a little bit. So we did a lot of pre-planning for that wire path, thinking through all of that, making sure that the wiring would work well before we ever assembled the first version of this. Okay, let's look at how the arm is actually done. This arm stack up is definitely a little complicated. It's coaxial so that the elbow and shoulder are both transmitting power through the same axis. It's not too difficult once you're able to see everything, so I'm going to hide a bunch of stuff so it's a little bit easier. There are a couple of encoder gears, so this encoder gear here will go up to an encoder on this side that's for the elbow. Then there's another encoder gear on this outside that goes to this encoder. For the one down here, this will be for the shoulder, so that we can sense them both independently. We can start seeing how some of that's going to work. Oh, that bearing made it hard. Okay. Let me see if I can get through that. Okay. So part of this that's important is that our shoulder isn't actually touching the max spline that it's riding on. So the shoulder sprocket, we put it on the lathe and we drill out a 1.5 inch diameter hole. And so it's able to just free spin around that shaft. The same is true for this encoder gear. It has a big enough hole that it's able to just free spin. And then in the arm itself, if I can hide some things, we can see in here that there are two bearings. So there's a bearing here, and there's a bearing over on this other side. And there's a bearing here. And so that allows this bicep to just be spinning freely on this max spline shaft. And so the sprocket here is bolted in through the 3D printed encoder gear, and that's how all of that motion is being transferred. And so even if this shaft isn't spinning, this sprocket can spin the bicep whenever it's needed. That allows this actual max spline shaft to be transferring the motion for our elbow. So this sprocket is directly mounted to the max spline in the normal way that it would, the way it's actually intended to be sold that way. And so it's whenever it turns this whole shaft. The outer sprocket down here does the same thing. And so it's able to turn on that shaft as well. And so that's how we're able to get motion from the motor way down here out through this arm shaft to this sprocket. And then this one drives another sprocket down here that's part of forearm. And this whole shaft again rotates with forearm. So the bicep itself doesn't actually interface directly with either of those max splines. It has bearings for rotation on both of them. And that has worked out pretty well for us. One of the things that we learned in 23 off season when we built a robot similar to this was that when we actually do the when we placed all the components and laid everything out with their exact widths and everything, we put in the snap rings exactly where those grooves are. As we started using the robot, it started actually being able to have more play. So there ended up like growing a gap between our sprocket or our last sprocket and the snap ring, and that meant everything could like shift around on the max spline. And it was causing us some issues. It would mean things were wiggling more than we wanted. It had a lot of play in it. And so what we came up in that year, we ended up coming up with a different thing where we had a hex shaft running through the spline, and we had bolts on the outside, and we could like tighten those bolts, and it would push everything together on top of the max spline. But we wanted to do that this year without having anything running through, so that we could run wires through the middle. And so what we came up with is this extra little aluminum plate here. It's tapped, so this is a 3/16 aluminum plate. It has tapped 1032 holes in it, and then those holes are lined up just on the aluminum of this back sprocket. So and the real one will only have 3 of these most likely, so that lets us center it pretty easily. And so as we tighten those 3 bolts, it increases the distance between this plate and the sprocket, and it takes up all the room that may appear in the max spline, or along that max spline shaft. So it allows us to not have any like hex collars or have to like remake or change out spacers if any of the things like push or change or stretch or whatever happens, kind of as the robot wears in a little bit. The other thing we did was we tried to make it so that it's all metal along this max spline. So we do have the 3D printed part here for between the arm and the shoulder, but beneath that is a metal spacer. There's a metal gear here for the encoder to sit on. Let me see if I can get it to show back. Yep. So yeah, so this encoder gear is actually sitting on top of a metal gear, and then you have the bearings. So all of that is aluminum or steel all the way across. So we're hoping it doesn't compress or change size like the 3D printed parts we had in 23.5 did. But we still wanted to be extra sure, and so we designed in the plate there. And then there's also one down on this one as well that we'll get to in forearm. The other thing, we've already done a whole blog post on this, so I'm not going to spend a ton of time on it. But we wanted to make sure these max spline shafts didn't bend or deform. We had some issues with that in 23.5 too, when you put a lot of load through them when you're using them as arm axles, especially when they're cantilevered. And so we had some issues where like this part of the max spline would like bend in a little bit, and these would change sides, and that would also loosen things up. And so for this year, we went ahead and we got carbon fiber tube that we run through the inside. So it's about a 1-inch OD and a 7/8 ID. And then we also have 3mm carbon fiber rods that we put in each of the little channels. And then all of that is glued in place with an epoxy. And so that makes the max spline far more stiff, and it makes it a lot harder to bend or compress any of these little channels or deform it, just because you have to physically move stuff if you do, instead of just being able to bend just the metal. You get a big stiffness upgrade, and it's a nice smooth channel for the wires to run through, and it seemed to work pretty well. It wasn't too expensive. The carbon fiber tube for one of our robots was only about $50, and then the individual rods are pretty cheap. I think we bought like a 15 pack for $30 or something, and they're 18 or 19 inches long. So that's more than enough for a single robot, I believe. Let's see. I think that's most everything for C. We have our temporary version of how we're going to mount the Quest catted out over here. They'll probably change a little bit before we finally do it, but something like that so it's rigid enough to not flex too much and let the Quest be able to see out the elevator side of our robot in a couple different orientations we're going to play with to be able to see if we can, how best to mount it. Miss anything? Oh, I did miss something. So the other thing, we talked about these chain tensioners and how we're going to do those with turnbuckles. One of the problems that we ran into early in the season was how we were going to tension this chain. Um, So our 23.5 robot only used its arm on one side of the robot. It wasn't double sided. It couldn't do things on both sides. And so for how long the arm was and for what motion it needed, it was easy enough just to have chain turnbuckles in here, and we could get enough motion from between the turnbuckles to do all of the things we needed with that arm. That's not true for this year. So because of the way this coaxial arm setup works, it makes programming it a lot easier, but it does make you have a little bit more motion out here because this sort of acts like a virtual four bar. So the because we're doing it all coaxial, the elbow motor, when you control its angle, it's controlling the angle of the elbow and everything independently of what the shoulder is doing. And so we can move the shoulder, and if the elbow is sticking straight up, it's going to stick straight up the entire time because you get the virtual four bar effect of this sprocket staying stationary, but this one moving around it. And so you get that angle adjustment for free basically. And so it syncs everything up much easier. But it does mean that this chain and sprocket moves a lot. And so we needed a way to have a tensioner that allowed it to continuously rotate, and when it caused the little turnbuckle to like crash into the sprocket teeth. Um, and so we had to invent a way to do that. We went through a lot of different options. Um, we've liked ratchet tensioning before. We've done the belt version, like we talked about a little earlier, a couple different times. We did that in 23 and 23.5, and that worked very well. I think Team 125 is one of the first teams to do it that way with a ratchet, and we borrowed that idea from them. And so we were like, okay, how do we do the same thing but for chain when we need to do a continuous? Um, and so we figured out if we just put a hex shaft in here, have a little standoff for the wrench to run into. The wrench is a little longer in real life. We're able to just twist this little like windmill, and it pushes one sprocket into this side of the chain, and it pushes the other one into this side, and it gives us a nice, easy way to tension it. We can untension super easily. You can push down a little bit and switch the lever over. Um, so if we need to work on it at all, we don't have to like take everything apart. We can just untension it, take the chain, swap it in and out, whatever we need to do. And so far in our pretty limited running, this has been working nicely. None of this is all that complicated. We made this a little bit thicker because this is the one that actually sits on the hex shaft. So we want to make sure that this plate doesn't slip on the hex shaft, as that's doing all the torque transfer from the plate into the ratchet. And then originally, we weren't sure how we were going to make these idlers. We've done a few different things where we've drilled out sprockets and put bushings and things. I believe right now it's just spinning on a 1/2-inch nylon spacer. So it's a 1/2-inch hex spinning on the 1/2-inch nylon. The sprockets aren't moving continuously very often, and they're just a tensioner, so they don't have a ton of load or anything on them. They're getting pushed in, but we should be able to replace that nylon tensioner or the nylon spacer pretty often. And so it's just a 1/2-inch one, so it takes up more of the room. So you just have the aluminum sprocket spinning on the nylon. And so far that's been fine. We have some other options if we need to, but that's really light and seems to just work. Okay. I think that's the end of C for now. Oh, the last thing, this bicep itself is made of max composite, again, because we want it to be pretty durable and give kind of a stiff outer frame. And then the inside here is just 3D printed nylon with chopped carbon fiber inside of it. And then that whole stack up is glued together. So it's 2 parts to be able to fit on our printer. So these are both printed on a Bamboo X1C. And so they have some little dovetails to connect together. We test printed some things to make sure we get a nice tight fit there. And then we use the same epoxy that we use to put in the carbon fiber tubes into the mech spline to glue up the dovetail, and then also glue the max composite faces to the arm itself. So this should give us a relatively stiff arm for the weight. It allows us to design in a lot of those features that we needed to, and mounting features and things, um, without having to machine them all into some form of a tube. If we needed to, most of this can be done on a 2x1, or sorry, a 2x2 piece of aluminum, and it would get close, but we'd probably end up still filling a good chunk of it with 3D printed things as well. It's a lot harder to machine. This worked out pretty quickly and allowed us to do a little bit more with the shape for the wiring, for adding in the tensioning and all of that. And so far has felt pretty good in our initial testing of it. Um, okay. Um, this is running a little long, but we'll still keep going. So this is the third mechanism, our corral for coral and algae. Um, Down here is what we call the forearm. So this is what kind of holds the whole claw mechanism together. We were able to, this is the same sprocket from C. So this is where it attaches down here. It's going to attach into this part of that chain. Um, it fully bolts all the way through here into the sprocket. So then all of the max spline is spinning. The sprocket here spins the max spline. It also spins this max spline shaft color back here. All of that is bolted to this 2x1, which is which is actually moving the rest of the assembly. This part is the same sort of expandable spacer concept that we talked about back here. We're able to screw in those bolts and expand the space along the max spline shaft to make sure everything doesn't have a way to wiggle or play at all. So you can push this up against the snap ring that's going to be behind it. And then we were able to build in this small custom gearbox that has a motor here that powers the twist. So this is what lets the claw twist around. And then it also has the motor here that actually powers the roller. And so all of that is coaxial again. So we run the twist power and the power for the roller through this same long axis out to the end of the arm. So that allows us to keep the motors back basically on top of the pivot, so we're not swinging that motor mass around and having problems there. Some of it's a little behind the pivot, so it's acting as a little bit of a counterbalance, not too much. We had to package it up tight enough just so we didn't hit things when we swing through near the belly band and near our drivetrain. The way this coaxial setup works is this is just a standard gearbox. You get the motor pinion going to here, and then this gear is a max spline gear, so it's turning the whole max spline shaft. On the back here, we have a motor belted over to a, this is a 1/2 inch to 3/8 hex adapter. And we have a 3/8 hex shaft that's running all the way through the middle of this max spline. This max spline again has that same carbon fiber setup and epoxy all the way through it, so it's extra stiff. Because this carbon fiber tube is 7/8 inch ID, it fits a rounded hex bearing perfectly for a 3/8 shaft, so we can run that 3/8 shaft all the way through. And so when that pulley spins, it spins the shaft all the way at the end over here. And so this is where the claw gets its power from. And so we also have another one of those max spline shaft collars here that's clamping it and bolting this piece of 2x1 to the end. And this gives us a mounting place for the claw to interface with. So we have all of these holes it can bolt into. This 2x1 allows us easy access to the shaft collar that holds in the hex shaft up on this end. And then there is a bolt down on the other end holding it from going too far out the other way. And then again, the snap rings are all set up here, kind of the same way we do on C. So the snap ring prevents the shaft from going too far that way. We have another one that we were able to cut into the middle of this ring as well. The nice thing about the snap rings here is you're not doing the entire diameter of the max spline. All of this is still fully aluminum. So we're not too worried about transferring torque through the snap ring, since the majority of it still it's not cut through. And so that holds this bearing in and kind of holds the plates together. And then there's one more all the way in here as well that we have to put in inside of this 2x1. The gearbox assembly is relatively simple. It's just a few plates. There's a printed standoff here to be able to bolt into a tube end cap. As we were going through trying to lighten things, we realized we could just use an L here instead of a tube end cap, and that gets us a little lighter. We still have the ability to put one in and bolt in there too if we think we need that stiffness. And then there's just a couple standoffs going all the way through to finish off that whole assembly. So yeah, again, relatively nothing too complicated, but it did take some good amount of time to make sure we could design it well. A lot of the sketching to keep these motors kind of in the same place to keep things semi-balanced. And then we do have a 1-to-1 encoder here as well for the twist. So there will be eventually a through-bore encoder there so we can know exactly where the twist is. Along with like a 3D printed spacer to keep that gear in place. A lot of this was designed to be super lightweight, so we don't even have the encoders and things aren't spinning in any bearing or anything, so there's no load on that. It's just spinning in the plates. We have a 3D printed standoff plate and the Max composite plate that we just cut the slightly larger than 13.75 millimeter hole here, and that can just spin inside there without adding too much friction or anything to the mechanism, but keeping weight dramatically down, because a lot of time was put into making sure all of this weighed as little as we reasonably could without dramatically changing our manufacturing processes or anything. All right, let's look at the claw. We've done a lot of iterations on how the end effector or claw or manipulator was going to work for this robot. We sort of went down the design choice of doing the double jointed arm and the elevator and everything before we knew for sure what this part of the robot was going to look like. This took a lot of testing. I don't think we got to this until 2 or 3 weeks ago, when we actually got to the finished version of having the coral manipulator be solid, having the algae manipulator be able to open, or the algae side of it, being able to do all of it with just a single roller. There were a lot of different concepts before that, but as we learned kind of what we needed and how we needed it to work, we were able to optimize a lot and get it down to the package that we are now. This is also part of the robot that'll probably see a lot more iterations as we continue through the season, as we test more, as we learn more, as we're able to make more and more fine micro adjustments to it to improve the robot. This is one of the places where that can happen a lot, as nothing else is built on top of it. Starting at the bottom here, this is where it actually mounts to the twist. And then we have a max 90 up here just to be able to change our direction from spinning the same way as the twist to being able to spin perpendicular to it. Right now we just have a normal max 90. We have designed in to be able to swap these plates of the max 90 to gain a little bit of weight back. So these are likely to become max composite in one of our versions. That'll also let us integrate the hard stop for the algae arm into these plates when we cut them out of max composite. And so that'll get it a little bit lighter. It'll allow us to take some standoffs out, or some bolts and hardware out, because this whole stack can be bolted together with the same bolts. The construction here took a while to figure out what we wanted. We knew we needed the coral to be able to be here. We knew we needed something to be able to have this arm open, but we didn't really know how to support everything out as wide as we needed to to be able to have these outside flanges that let us center the coral. That was another one of the big challenges for this robot, was how do you hold the coral how we want it without, and actually know where it is if we're scoring on the front and back and everything. And so we saw a couple videos early on, probably in that first few days of the season, that let us see that if you have a roller and like a smooth-ish surface over here, and you don't let it come in on this side, it will gain some sort of like screw effect, and as it's being spun, it'll slide in before fully sliding down. And so we've been able to optimize that a little bit more, and work through this 6-plate construction where we have the 2 outer plates here, these 2 sort of lower widening plates, and then our horseshoe U plates out at the end that allow the actual scoring to happen, because we have to leave that opening of the coral there for us to be able to put it over and onto the reef branch. The belt for this, to be able to get around things, you couldn't go just straight. It would get in the way of like holding the algae, so we needed to add a little idler sprocket here, or idler pulley here, sorry. Right now it's just spinning, it's a printed pulley just spinning directly on a hex shaft. Actually, I think right now on robot it's a printed pulley just spinning on a nylon spacer. We have plans to be able to put a couple really tiny bearings in here that we're able to bolt in and have this pulley spinning on tiny bearings. And then we also have some small bearings out here that are 5mm ID, 19mm OD, which ends up being basically 3/4. And so that's able to make this shaft spin on bearings as well without having this plate be too big for a 1-inch or 1 1/8 inch bearing. It also lets maintenance be a little bit easier. You can just pull those 2 bolts and the whole shaft can just come out, and you can change whatever you need to instead of sliding the wheels around all the time. Um, we use a lot of laser joint and T-slot construction. So since the Max composite can be laser joints or laser cut so easily, this lets us build some nice structures pretty quickly here, and it's very durable. We have some parts mounted that aren't in the assembly yet here, where we have some 3D printed parts that stiffen this up. We found that because the belt tension was being pulled here, these plates could kind of flex down and allow this to get closer, and then the belt would be slipping. So we printed some 3D printed parts that bolt in to these outer holes here, and then across the bottom here and get bolted in and up to there, and that stops a lot of the flex, but still allows it to be quite lightweight, because the print can be very, very light, but still has that height there and thickness that makes it harder to bend without adding a lot of mass. So there'll still be some more optimizations to do. We did some things to make sure that the reef branches could never get stuck like between this gap. That's another thing that this 3D printed part does, and another 3D printed part up here that stiffens up things a little bit too, just so that if we accidentally ever get the robot in some weird spot, we don't want to catch on one of the branches in some way and like rip our arm off. That would be very sad. The algae side is just a simple lever with a spring. So there's a torsion spring here that's always pushing it closed, and then as the algae comes in, it basically, the algae itself opens this up and it runs into the hard stop, which eventually will be this little plate. Right now there's a cable that's bolted from here that loops around this standoff, and so that lets us have a hard opening, and so the algae is able to squeeze in between our algae bar and these rollers, and it's able to pinch it and hold it quite nicely. One of the reasons we need this to be able to be as small as it can is when we go to score the coral, this bar has to pass the other coral that's on the other side. So this whole mechanism is designed around the idea that the robot can be centered with the center of the twist and the arm right here, like above the April tag between the 2 reef branches. And so when it's centered this way, this coral is lined up to the left reef branch, and then if we just flip it over, then it's lined up to the right reef branch. So that lets us have a single alignment for each face of the reef where we can score the coral, grab the algae if it's in one of the up or down positions, or score the coral on either one of the branches. And that so far seems to be working pretty nicely as well. And that was a lot of how we had to develop this, was to get this small enough to not hit the other coral, as the two reef branches are only 13.5 inches apart. So you have to basically leave enough room for another coral right over here. Um, okay, I think that's everything for corral, or most everything. We're using West Coast Products 1.625-inch wheels. We're still not sure exactly which durometer. I think we have 45s on there right now. But there's some discussion about trying out some of the stiffer ones and seeing if that's better, or the softer ones. Same with like how many wheels and things. All of that will be iterated pretty quickly throughout the season. Same with like spacing and things, because there may be spacing that's slightly better for coral or slightly better for algae, and we can work through that as the season goes on. Okay, one more mechanism. This video is running long, but it should be all right. Incline. So this was kind of our mid-season biggest change. Originally, this was two different mechanisms. We had an algae intake on one side of the robot and a climber on the side where this ended up. So the climber was always planning to be over here opposite the elevator, but then the original plan was to have an algae intake over here that would be tucked down. But then we realized trying to like fold them on top of each other potentially, just trying to make sure the algae intake stayed out of the way of the arm, it was getting more complicated than we needed to. Team Scream was sort of the original inspiration for being able to combine them and just being able to have this form of a climber anywhere, where you kind of go under the cage. Let me see if it loads. Oh, it might be a little backward. Oh, it loaded super backwards. All right, that's not a good picture right now. It was set up at some point to show it climbing. Oh, that's a little bit better. So you basically go under the cage, and then as this comes up, this pulls you back, and you're able to be climbed. The arm will be out of the way somewhere. We'll figure that out. And you're able to pull the cage back and get the robot off the ground, while still using that same mechanism to potentially be able to do algae intake and coral intake, and be able to score coral on level 1 if we need to. So this gives us a little bit of redundancy. The claw is able to do a lot. We think we might be able to ground intake coral and algae with it as well. We don't really know. It's not fully optimized for that. If it can do it, great. If there's some small tweaks we can do to make it better, that'll be fine too. But there may be some matches where something breaks out here and we still need to be able to do things. It might be really fast just to be able to flick this out, grab a coral, score it into L1. Similarly, if we have to go to the other side of the field and grab an algae, if we're trying to steal algae to be able to score it in our net, we may want to use this mechanism instead of our arm, as this should be a little bit more durable if we have to like run it into other robots' intakes or anything like that, or run it into a wall. It's a relatively simple mechanism. We have two motors here on a gearbox that drive the pivot. Overall, it's about 100-to-1 reduction out to the arms on these sprockets. We drive both sides of them, as this gearbox has a jack shaft with the sprocket on this end that drives out to this side that has a sprocket here. Both of these are tensioned because we only have a single bolt mounting the gearboxes here. And then we have these turnbuckles that we're able to tighten, and those increase the spacing of this chain run and allow us to tighten that chain and get us a nice tension there. And then we have a motor out on the arm, but close enough to the pivot that when it's folded out, it still basically sits right on top of our bumper, so it never leaves our frame perimeter. And it's belted up to this front roller that then has a gear and a belt down to the smaller one that we use for algae. So the coral's basically able to sit between these three shafts after we intake it, and then the algae is able to pull in over our bumper and sit kind of between these wedges and this roller right here. Um, Conceptually, it's set up to where we can do handoffs if we need to. If there's an algae here, we can fold this all the way back. We can have the arm raise up and come get the algae out of there. We don't know how often or when we'll get that stuff set up. It's not the highest priority. We did build it to be able to do it. It can do the same thing with coral. It can come get one of the coral out of here if it needs to, but a lot of times it may just be picking up the algae or taking the coral to level 1. An algae handoff may happen, is more likely to happen, but early on it might just be grabbing algae, putting it in the processor if we need to, or we could even like spit it out, grab it with the other arm to take it to the net if we needed to or something. That would be a little slower, but it's all possible if we don't get the handoffs working as well as we want. The other nice thing about the potential for the handoffs is it allows us to hold both game pieces at the same time if we need to. So we could have algae up in our claw and then coral down here. And there's some times where that might be advantageous, depending on the cycles we're doing, how we're cleaning things up. It might make sense to do that, or the other way, we could have coral in the claw and algae down here. It does give us some place where we could potentially store them, depending on how the game all plays out. There's a few different strategies and things that may make that beneficial. One of the last parts about this, oh, I guess that we can look at the climb before we look at that. So the climbing system, basically this wheel and this shaft go under the cage. They're a little bit tall when we place it all the way down directly, but we'll have these wheels spinning in, so it should basically like pop the cage over. Even if it doesn't, driving into it seems to work pretty well. We've done that test a couple times already. And then it drives in, it kind of funnels between these two plastic funnels here, so we can get it mostly centered. These may change, we may change these dimensions and things throughout the season. And then it just pulls back, and then we have a small little plate here that gets bolted. It's very likely part of our bumper mounting system, and so it'll get bolted, and the bottom of the cage will come in under here, and that'll stop the cage from rising, similar to how the Everybot has their little bolts for feet as well in their climb. That pulls the cage back like that. In our initial tests, we weren't entirely sure how strong the brake mode was on these motors. We didn't necessarily think it was going to be strong enough, but we wanted to test it first to be sure. And we did, and it wasn't strong enough to hold us up for the 5 seconds after the match. So over the last few days, we've been developing a ratcheting system that will allow us to have a little servo that just engages this ratchet right on the motor shaft here. So it's the farthest reduction, so it sees the least amount of load while still being able to stop the mechanism. And so when it's engaged, this ratchet won't be able to rotate back and have it unclimb at all. So basically throughout most of the match, this will be pulled forward. Not assembled correctly yet. This will be pulled out of the way. This can just free spin in whatever direction we want. Then when we go to climb, we'll engage this. There's a little spring on it that'll allow us to put the arm down nicely. And then as we pull it up, it will, or actually we'll, once we, sorry, I said that in incorrect order. Once we put it down, we'll engage the ratchet. It will allow us to close it, and it'll rotate that way, but it won't allow it to open back up at all, holding us up till after the match, when we can then come in and either manually release this, is the most likely option. We'll be able to push that and then just open up the cage and take the robot off of the cage at the end of the match. That is the plan. Okay, so that's pretty much every mechanism. Mechanically, we have our practice bot finished. The CompBot drivetrain is done, and elevator is going on, I think, as I speak right now. And then we'll be able to finish up building the rest of this. There's still a lot to tweak. This is a long season. Um, but things are looking pretty promising right now. That it's going to do most of what we designed it to, and we'll be able to do quite a bit more software tuning to make it better as the season goes on. And that was a lot of the design ideas for this, is to give us enough room that even as we finish the mechanical development, there's still more we can improve as we do the control side as well. All right, I think that wraps it up for this video.